Students, let us discuss about tolerance stack-up analysis in this session. Shown here is an assembly of shaft and housing. This assembly has got 7 number of parts. The last part to be assembled is the circlip, which is shown in green color. The circlip is the last part to be assembled in this assembly. Once the circlip is fitted in the groove on the shaft, the axial play of the bearing has to be fully arrested. So the purpose of fitting a circlip in an assembly is to arrest the axial play. Let us see how the sequence of assembling each part later. We want to find the axial play between the circlip. So between the circlip and the bearing using Surefit law and normal law. So ideally there should not be any axial play between the circlip and the bearing. So the purpose of fitting a circlip is to arrest the axial play. But practically, when the tolerance are assigned to various parts of the assembly, there exists a small axial play between the bearing and the circlip. So this axial play we want to investigate using a Surefit law and normal law. For finding the axial play, we have to draw a dimension loop over the assembly. So before drawing the dimension loop, let us see how to assemble the parts. What is the sequence in which the parts are being assembled? Now this is the main part, the housing. Cast iron housing is the main framework onto which we are assembling each and every parts. Now this is the circlip. This is the circlip which is assembled as a last part in the assembly. So we have to use a plier for opening the circlip, then you have to fit it in the groove on the shaft. Now this is sleeve. The sleeve is used to fit the bearing into it. And we are using 2 number of sleeve for each assembly. Similarly, bearing, we are using 2 number of bearing for each assembly. Now first, one bearing is fitted onto the shaft. So coming to the sequence of assembling the parts, first thing is we are fitting one bearing fitted from this end, moved from this end, and it is moved until the bearing is touching on the shoulder of the shaft. Next, on the frame, on the housing, cast iron housing, we are fitting the sleeve, 2 number, one this side and one this side. So the 2 sleeves are fitted on either end of the housing. Then the shaft fitted with one bearing is inserted from the right side. It's inserted from the right side, and one more bearing is fitted from this side onto the shaft. The last part is the circlip. The circlip is then fitted onto the groove of the shaft as a last part. So once the circle is fitted, the axial movement of all these parts has to be arrested. But due to various tolerances assigned to the parts of the subassembly, there exists a small axial play which we want to find out by applying the Surefit law and normal law. So these are the various dimensions on the part drawing of the assembly. So this is the housing, main housing. So I have shown 2 dimensions, E and D. The remaining diametrical dimensions I have not included here. On the shaft, there are 4 dimensions, A, J, B, C. J is the width of the groove. This groove is machined on the shaft for fitting the circlip. Circlip thickness is K. And sleeve, on the sleeve we have got 3 linear dimensions, G, H and F. Again, the diametrical dimensions are not shown in this drawing. Bearing width is L. So these are the values of the various dimensions of the part drawing. The mean value of A is 260 and the tolerance is plus or minus 0.26. Tolerance on this dimension A is plus or minus 0.26. The mean value of dimension B is 230 plus or minus 0.2. 500 plus or minus 0.5. So the mean value and the tolerances are shown in this table. All the tolerances are shown as equal bilateral form. If there is any dimensions which is having non-equal bilateral or unilateral dimensions, we have to convert into equal bilateral form before substituting in the equations. So here all the dimensions are having equal bilateral form. So there is no need to convert here. Now let us see how to draw the dimensional loop over the assembly to find out the axial plane. For drawing the dimensional loop, we have to take an origin. Now the play is the distance between the end of the circlip and the bearing. So this is the axial play. So either any one end of this axial play is to be considered as origin. So let me take the right end of the axial play as the origin for my loop, dimensional loop. So the origin is shown as a cross mark. So the right end of the axial play is the origin. So now the bearing surface is the origin. Okay, the bearing surface is the starting point of this axial play. And the other end of the axial play is touching on the circle. So this axial play I want to find by applying the Surfit law and normal law. So this is the origin. From the origin, if I move towards left side, let me take a convention of minus. From the origin, if I move towards the right side, I take a convention of positive. Let us start making the loop. From origin, I am making the loop. First it is moving over the axial plane. Okay, from the origin, I am moving towards the left side. Okay, until coming to the end of the circle. So minus axial plane is the first element in the dimensional loop. Minus AP, minus axial plane. Then from the end of the circlip, I move to the other end of the circlip. So that is this dimension. Okay. So the second element on the dimensional loop is the thickness of the circlip. So that is minus K. So K is the thickness of the circlip. So since I move towards the left side, I take a convention of minus K. So while you draw the loop like this, some points you have to notice. First, the loop has to be drawn only over the known dimensions only. So these are the dimensions which are available on the part drawing. So the loop has to pass through the known value of dimensions only. Suppose if the loop is trying to pass from this end to this end, there is no dimension prevailing here. Okay, so if I try to draw a loop, okay, moving over this point to this point, so there is no dimension here. So we have got only two dimensions, E and D. So the loop cannot be drawn to move from this point to this point. There is no dimension here. So that is the first rule we have to follow. The second rule is, when you try to assemble all the parts, suppose the bearing is fitted. So bearing is pushed until it is touching on the sleeve. So the loop is passing from one component to other component through the point of contact between the two parts. So this is the other point which you have to note. So when you try to draw the loop, from one point to other part it has to jump, so only through the point of contact between the two parts. So the second element is minus k. From the end of the circle, let me move over to the dimension of the shaft. So on the shaft there is one dimension b. So now I have come to the end of the circle. The circle is butting against the surface on the groove. So from here plus b. So b is the next dimension on the loop. So b is one of the dimension of the shaft. So plus b. So let me draw the b. Now from okay, so the third element is so plus b. So plus b. Since I move towards right side, it is plus b. Then on the shoulder of the shaft, bearing is touching. So now let me move over to the bearing. So from the shoulder minus, so bearing with is L, minus L. Okay. So from the shoulder, I move over to the next component, that is the bearing. So bearing with is minus L. So minus L. Now I have come to the bearing. So from the bearing is touching on the sleeve. So on the sleeve we have got a dimension F. So F is the one of the dimension on the sleeve. So let me move over to the dimension F. So plus F. So I have drawn the plus F. Okay. Now I have come to the end of the housing. So the sleeve is touching on the housing. So now I move over to the housing. So from here I move over to the other end of the housing. Other end of the housing is, so what is the dimension? This is minus d. So d is the length of the overall length of the housing. So minus d. Now I have come to the left end of the housing. So on this surface the sleeve is touching. So the sleeve, on the sleeve we have got dimension F. So F is the dimension on the sleeve. So plus F. So plus F I have written. Now I have come to the sleeve. On the sleeve a shaft is bearing is touching. So the bearing width is L. Bearing width is L. Okay. So since I move towards the left side, I have to put minus L. So minus L. Now I have started the loop from this point. Okay. So one end of the bearing. Again I have come back to the same point. Okay. So I have started making the loop from one end of the bearing. Again I have come back to the same point. So the loop closes now. Okay, here the loop closes now. So is equal to 0. So now these are the elements for which the dimensional loop passes through. Minus AP minus K plus B minus L plus F minus D plus F minus L equal to 0. So once I have drawn the loop, then I can find the answer by applying the Surfit law or normal law. So this is the dimension loop drawn over the assembly in order to find the axial plane. So AP is the axial plane. So here AP is what we want. So that is taken to the left side, and this is the I am getting minus K plus B minus L plus F minus D plus F minus L. On substituting the nominal value from this table, I find the mean value of axial plane as 1 mm. To find the Surfit variation about the axial plane by applying the Surfit law, let me add this tolerance of the individual dimensions. So these are the 7 dimensions that are found to be affecting the axial plane: K, B, L, F, D, F, L. So what are the tolerance of these 7 dimensions? So all those tolerances are added. So small k, small b, small l, all these are tolerance of the individual dimensions which are found to be affecting the axial plane. So when you find the sum of these 7 dimensions, the tolerance of 7 dimensions, we got the answer as 0.57. So as per Surfit law, the axial plane is found to be 1 plus or minus 0.57. Now let us apply the normal law. So the mean value of axial plane will not change. Okay, but we got the answer as 1 by applying the looping technique. So that won't change. Tolerance or the variation of the mean axial plane is found by taking the square root of the sum of the square of the individual dimensions. Okay. So this is the variation about the mean axial plane, which is equal to square root of k squared plus b squared plus l squared plus f squared plus d squared plus f squared plus l squared. So on substituting the values, we find that the variation about the axial plane, variation about the mean axial plane is 0.29. So this is the answer as per the normal law. Axial plane is found to be 1 plus or minus 0.29 as per the normal law. So the assumption that we have made by for applying the normal law is process follows plus or minus 3 sigma quality, and all the dimensions are following normal distribution with its mean centered around the limits. So we assume the centered processes for all the dimensions. So under these 2 assumptions, we got the answer as 1 plus or minus 0.29 when we apply the normal law.